For centuries, humanity has looked to the night sky and seen a king, Jupiter, a brilliant point of light that, through a telescope, resolves into a world of impossible scale and beauty. It's the titan of our solar system, a majestic giant so vast that all the other planets could comfortably fit inside it, and what we see is a masterpiece of celestial chaos, elegant, swirling bands of cream and caramel-colored clouds, punctuated by colossal, rotating storms. It's a familiar image, a planet defined by its beautiful, violent weather. We've all seen the pictures. We've marveled at the Great Red Spot, a tempest that has churned for nearly 200 years. But this is just the skin of the gas giant. This is the veil. The real mystery, the one that has puzzled scientists for generations, is what Jupiter is hiding beneath its clouds. For decades, we could only guess what was under those swirling storms. But new data, much of it from NASA's Juno spacecraft, has finally allowed us to peel back the layers. And what we've found is a bizarre and alien world that we never, ever expected. A world with an ocean larger than any on Earth, but an ocean made of metal. A world with a core that isn't solid, but fuzzy and diffuse, rewriting the very story of how planets are born. So, let's take a journey deep into the heart of the King of Planets, to uncover the secrets Jupiter has been hiding. The atmosphere we can see before we dive in. Let's appreciate the world we see from the outside. The face of Jupiter isn't a solid surface. As a gas giant, it has no true ground to stand on. What we see are the tops of its highest clouds, a complex, three-tiered system stretching down about 44 miles, or 71 kilometers. The lighter zones are areas where gas is rising, and the darker belts are where gas is falling. They're like colossal weather fronts wrapping around the entire planet, driven by ferocious jet streams. And these aren't gentle breezes. The winds on Jupiter can top 400 miles per hour, or about 650 kilometers per hour. But here's where it gets really strange. This entire atmospheric system makes up less than 1% of Jupiter's total radius. It's a thin, decorative shell. To understand what Jupiter is truly hiding, we have to leave this familiar territory behind and plunge into a realm of unimaginable pressure and temperature. Data from the Juno mission shockingly revealed that these jet streams aren't just skin deep. They plunged 2,000 miles down, about 3,200 kilometers, deep into the planet. We still don't know the exact mechanism driving them, but it seems to be connected to the movement of ammonia gas deep within the atmosphere. Think of it as a layered cake of cosmic proportions. The highest layer, giving Jupiter its pale, creamy colors, is thought to be made of frozen ammonia ice crystals. But recent studies suggest it is not the same storm that astronomers like Cassini saw back in the 1600s. That one likely vanished, and this one formed sometime after 1831. Calling it a storm almost feels inadequate. For a long time, we thought it was a surface-level event, like a giant hurricane. But here again, Juno peeled back the veil. The Great Red Spot is a towering monster, with roots extending more than 200 miles, or 350 kilometers, deep into the atmosphere. While it was once big enough to swallow 3 Earths, it has been shrinking for decades and is now just a little wider than our own planet. Beneath that, a layer of ammonium hydrosulfide crystals, and deeper still, a layer of water, ice, and vapor. The planet's famous stripes are called zones and belts. And then there is the Great Red Spot. It is the most iconic storm in the solar system, an anticyclone that's been observed for almost 2 centuries. But even this, the deepest storm ever measured, is only scratching the surface. Plunging through the gas. Alright, let's begin our descent. As we move past the ammonia and water clouds, the light from the sun fades to black. We are in perpetual darkness, and the environment gets extreme, fast. On Earth, hydrogen is a light, simple gas. But here, it starts to get weird. As we descend, the pressure builds to hundreds of thousands of times that of Earth's atmosphere. The hydrogen gas is compressed so intensely that the line between a gas and a liquid just disappears. It becomes a bizarre state called a supercritical fluid. It flows like a liquid but has the density of a gas, a soupy, turbulent medium, getting hotter and denser with every kilometer we fall. The pressure and temperature are both increasing at a staggering rate. With every mile we drop, the weight of the atmosphere above us squeezes and compresses everything. Now, multiply that by another 1,000. And another. That's the kind of environment we're in. It's enough to crush any spacecraft ever built, which is why we rely on indirect methods, like Juno's gravity and magnetic field measurements, to see what's down here. We are now thousands of kilometers below the cloud tops, traveling through a dark, hot, soupy ocean of supercritical hydrogen. The temperature has hit thousands of degrees Celsius, hotter than the surface of some stars. The temperature also climbs, not from sunlight, but from the immense pressure and the heat left over from Jupiter's formation 4.5 billion years ago. In fact, Jupiter radiates almost twice as much heat as it gets from the Sun, a sign the planet is still slowly contracting under its own gravity. As we continue to fall, we approach a boundary point where the pressure becomes so overwhelming that it fundamentally rewrites the rules of chemistry. We're about to enter the largest ocean in the entire solar system. The atmosphere here is mostly hydrogen and helium, the same stuff the Sun is made of. Imagine the pressure at the bottom of the Mariana Trench, the deepest point in our oceans. It's about 1,000 times the pressure at sea level. But things are about to get even stranger. The largest ocean in the solar system, as we cross this threshold, the pressure becomes so colossal that it physically rips hydrogen molecules apart. But it does something even more incredible. It squeezes the hydrogen atoms so tightly that their electrons are forced out. These electrons are no longer tied to their atoms. They're set free, forming a sea of free-flowing electric charge. In this moment, hydrogen, the most common element in the universe, stops being a gas and becomes an electrical conductor. It becomes a metal. We are now floating in an ocean of liquid metallic hydrogen. Juno's instruments don't see the ocean directly, but they measure its profound effects, the biggest of which is Jupiter's immense magnetic field. It's a magnetic field nearly 20,000 times more powerful than Earth's, and it's generated right here. As this vast, electrically conducting ocean swirls with the planet's rapid 10-hour rotation, it acts like a gigantic dynamo. This planetary dynamo creates the most powerful magnetic field of any planet, a structure so large that if we could see it from Earth, it would appear bigger than our full moon. That's not a metaphor. It is a literal ocean, the largest in the solar system, but its liquid isn't water. It's hydrogen behaving like a molten metal. It's a tough concept to wrap your head around. The field is lumpy and irregular, with strange hotspots like the Great Blue Spot, an area of intense magnetic activity near Jupiter's equator. These quirks tell scientists about the complex, turbulent flows happening deep within the metallic hydrogen sea. But our journey isn't over. As we descend through this swirling metallic sea, we approach the planet's very heart. And here Juno would make its most shocking discovery of all. Imagine a planet-sized vat of super-hot liquid mercury, but made of the lightest element in existence. It is dense, it is scorching hot, and it churns with powerful convection currents, carrying heat from the planet's deep interior outwards. This layer makes up the bulk of Jupiter. It is an alien state of matter that we're only just beginning to understand through hyperpressure lab experiments and computer simulations. The existence of this ocean was predicted back in 1935, but it was NASA's Juno mission that gave us the best evidence for its nature and scale. Juno's detailed mapping of this field has given us our first real glimpse into this hidden ocean. The big reveal part 2 for decades, the textbook model of how Jupiter formed was pretty straightforward. Scientists believe that early in the solar system's history, a solid core of rock and ice, maybe 10 times the mass of Earth, formed first. This giant seed then used its gravity to quickly pull in the hydrogen and helium gas we see today. These measurements allowed scientists to map how mass is distributed deep inside the planet, and the results were stunning. They didn't show a small, compact core. They showed there was no distinct core at all. So, according to the model, we should find a small, compact, well-defined core at the center distinct ball of heavy elements, completely separate from the metallic hydrogen ocean. This was the leading theory for how all giant planets were born. But the universe is rarely that simple. As Juno repeatedly swooped over Jupiter, its instruments measured tiny variations in the planet's gravitational field. Two dramatic theories have emerged. This model proposes that Jupiter didn't form in a neat two-step process. Instead, it grew by collecting gas and solids at the same time. As rocky and tar-like materials rained down into the growing planet, they didn't all sink to the center. The intense heat and churning of the interior could have dissolved and mixed them as they fell, creating the diluted core from the very beginning. The planet's interior is far more complex, dynamic, and mysterious than we ever imagined. Instead of a solid ball, Juno's data points to a core that is fuzzy, dilute, or dissolved. This is the second great secret Jupiter was hiding. The heavy Alamunster rock, metal, and ices are, instead, mixed and smeared out across a vast region. This fuzzy core might start halfway into the planet and extend all the way to the center, containing anywhere from 7 to 25 Earth masses of material. but blended in a gradient with a metallic hydrogen. It's more like sugar dissolving in coffee. This discovery has forced scientists to completely rethink how giant planets form. One model suggests that about 4.5 billion years ago, a young Jupiter collided head-on with another massive protoplanet, maybe 10 times the mass of Earth. This incredibly violent impact would have shattered Jupiter's original, compact core. The debris would have then mixed with the hot, dense, metallic hydrogen, creating the spread-out, fuzzy gradient Juno sees today. In this scenario, Jupiter isn't just a king, but a cosmic cannibal that swallowed another world, with the evidence hidden in its very heart. So, what could create such a strange core? The first is a cataclysmic, ancient impact. The second theory suggests the fuzzy core is a relic of Jupiter's unique birth. Whichever theory is right, the conclusion is the same. The old, simple picture of Jupiter is gone. What these secrets tell us, uncovering these secrets stir metallic ocean, and the fuzzy core does more than just satisfy our curiosity. It changes our understanding of our solar system and the thousands of giant planets we're rediscovering around other stars. Jupiter is a time capsule. Because of its incredible size, its composition is thought to mirror the original gas and dust cloud that formed our sun and planets. By studying its interior, we are looking back in time. The dynamo that generates Jupiter's magnetic field is a powerful shield, protecting the planet and its moons from the harsh solar wind. But it's also a blueprint. When we detect magnetic fields around distant exoplanets, we can now infer they might have a similar exotic ocean churning inside. Its immense gravity has shaped the orbits of the other planets and acts as a cosmic vacuum cleaner, deflecting countless comets and asteroids that could otherwise threaten Earth. This influence is a direct result of its mass, and how it has distributed a distribution we now know is defined by this strange, layered interior of gas, liquid metal, and a dilute core. By understanding what's inside Jupiter, we better understand our entire planetary neighborhood. The physics we're learning at Jupiter is becoming a universal translator for giant planets everywhere. The discovery of the fuzzy core throws a wrench in the standard model of planet formation. If Jupiter, our archetype, didn't form with a simple, solid core, then maybe other giant planets didn't either. Astronomers now have to consider these new, wilder scenarios when they look at hot Jupiters and other gas giants across the galaxy. It challenges the very definition of a planetary core, and understanding the liquid metallic hydrogen ocean is critical. These discoveries also help explain Jupiter's role as the solar system's great protector. From the outside, Jupiter is a familiar swirl of storms and clouds. But beneath that veil, a universe of extremes lies hidden. Our journey took us through layers of ammonia ice, into a dark, crushing abyss of supercritical gas. We plunged deeper still, into the largest ocean in the solar system, a turbulent sea of liquid metallic hydrogen that generates a magnetic field of unimaginable power. We've replaced old theories with new, stranger realities. But for every question answered, new ones have emerged. What really happened in that great impact? How exactly do the heavy elements and metallic hydrogen mix? How deep do the roots of the storms really go? Jupiter has shared some of its secrets, but the king of planets is not done surprising us. The journey of discovery is far from over, and at its heart, we found not a solid ball, but a ghost, a diffuse, fuzzy core that speaks of a violent birth or a mysterious formation, a secret that rewrites the story of how worlds like this come to be. Thanks to NASA's Juno mission, we've peered beneath the clouds for the first time.